Well, in this slideshow and video, which lasts for about 20 minutes, we'll be looking at the history of landfalling severe tropical cyclones on the east coast of Queensland, particularly in the last 50 years. We'll also be looking at possible trends in the numbers of these storms and the implications for design of structures according to Australian standard AS NZS 1170.2. Well, this slide shows part of the map from AS NZS 1170.2, the map of wind regions, showing the Queensland coastline that we're talking about. The red line there is sort of a smooth line along that coastline, showing there's about 1,800 kilometres of Region C on the east coast of Queensland there. From the south in around Fraser Island, almost up to Cape York. So 1,800 kilometres, where in the past, of course, we've had a number of tropical cyclones impacting along that strip. Well, the Bureau of Meteorology has got a very useful interactive website in which you can show the number of cyclones or their tracks for certain parts of the coast. This is for about a 50-year period, 1969 to 2018, showing all the tracks within 500 kilometres of Townsville. It's not quite the whole of that 1,800 kilometre strip, but most of them would be covered by that chart there. So there's a lot of spaghetti showing there. One of them in the middle there, that red one, is Cyclone Yasi, which was probably one of the most famous in that period, did a fair bit of damage. We'll talk about that one later. Well, after Cyclone Yasi, which happened in February 2011, there was a lot of surveying of the strip of coastline that was affected and estimates made of the peak gust that occurred during the passage of the cyclone as it crossed the coast. And this is a chart showing the contours of that estimated maximum gust. By the way, this is a 0.2 second gust as used in AS NZS 1170.2, which is a bit higher than the what the Bureau normally calls. So you see those contours there with a maximum value affecting about 10 kilometres of coastline in the Cardwell Hinchinbrook Island area of about 10 kilometres. This is probably fairly representative of the sort of contours that you would get and the strip which would be affected by the maximum winds for a cyclone of a category 4 or 5 category crossing the coastline there. So effectively 10 kilometres of coastline is affected by quite a high wind speed, which happens to be about the 500-year average recurrence interval in AS NZS 1170.2 for Region C. Well, the previous slide showed the footprint of contours of maximum gust produced by Cyclone Yasi back in 2011. And this can be regarded as typical of an impact of a severe category 4 or 5 storm. Now that produced a 10 kilometre strip on the coastline of 65 metres per second gust or greater. And that is a gust at a standard height of 10 metres over land, over rural land terrain. So it's interesting to compare that with what we have in AS NZS 1170.2 for Region C. Now the value in 1170.2 for Region C, V500, 500-year average recurrence interval, is 66 metres per second. So what that's suggesting is that if the region boundaries are correct, that every point along that 1,800 kilometres of coastline would see 66 metres per second once in a 500-year period, on average. So we have 10 kilometres being affected by a single storm. So how many storms would that take to produce every point along that coastline to see that value of wind speed? Well, it's pretty obvious it would be 180 storms, with each one with a 10-kilometre range, affecting the whole of the coastline over that period. So in 500 years or 50 decade, the standard 1170.2 expects 180 landfalls of category 4s and above. That works out to be 3.6 per decade. Now, this is interesting to compare that figure of 3.6 per decade of category 4 and 5 with what Jeff Callaghan and Scott Power from the Bureau of Meteorology came up with about back in 2010. They wrote a paper. You can see the title there, Variability and Decline of the Number of Severe Tropical Cyclones Making Landfall Over Eastern Australia Since the Late 19th Century. So they went back to 1872 and counted them, tracked them up to 2010 when this paper was written. And their categorization was categories 3, 4 and 5 cyclones. And they come up with an average of 3.1 per decade. So it's in the same ballpark as the 3.6. But you have to remember that before about 1969 or 70, before the satellite information was available, a lot of cyclones probably wouldn't have got tracked, especially at the late 19th century era, where the population was much less. So it probably was higher than that figure of 3.1 per decade. The other thing to note there is that since 2010, we've actually had 4 confirmed category 4 or 5 cyclones impacting. We'll talk about those later. So they weren't included in that figure. Now this table shows the number of tropical cyclones of category 3 and above that made impact on that Queensland coast over the 50-year period from 1970 to 2020, 5 decades. Now that was the satellite era, so these are quite accurate figures. Some of the categories were changed based on more recent information. But this is a fairly accurate table. So 18 category 3 and above cyclones impacting the coast over 5 decades, that's 3.6 per decade. By coincidence, that's actually the same figure we had a couple of slides ago, based on the footprint and the wind speed from AS NZS 1170.2. Now this is the same table, but now we've highlighted in red the cyclones that have made impact with category 4 and 5 intensity. These are the ones that will do the damage, which even for buildings that have been designed according to the standard 1170.2. So you see those in red there. Now there's 5 of them in red, and there's another 3 that I've got question marks there. They could be category 4. They're either 3 or 4. So we've either got, over that 5 decades, 5 or 8, somewhere between 5 and 8 very severe tropical cyclone impacts over the 5 decades. So that's only 1.0 to 1.6 per decade. Interestingly though, the 4 of those impacts in red there came in the last decade, from about 2010 to 2020. And only before that, there was only about 1 a decade at the most. Now on this slide, we're focusing on the 4 very severe tropical cyclones that made landfall in the years 2011 to 2020. Yazi, Ita, Marcy and Debbie. These were very strong events. They all did some damage. But the point is, we've had 4 of these events in the 1 decade. Whereas, as we saw on the previous slide, the average over the previous 4 decades was less than 1 per decade. So this decade, 2011 to 2020, was obviously exceptional. Now, the computer modelers will tell you that we expect to get more severe tropical cyclones occurring as a result of increasing carbon dioxide in the atmosphere. This may be happening, and certainly we're getting similar events happening in other parts of the world with hurricanes and typhoons increasing in strength. Well, how can we model this probabilistically? Now, the right probability distribution for discrete or integer events, such as a number of impacts of severe tropical cyclones on a coastline, is the Poisson distribution, which is quite a simple function, as you see there. X is the number of events. In this case, it's the number of coastal crossings by tropical cyclones within a decade. There is only the one parameter for the distribution, and that's lambda. So that's the average number over in a decade. So for this particular situation we have here, lambda up to about, based on the information up to 2010, was about 1.0. The question is, what is the probability of getting 4, x equal to 4, within the last decade, which appears to be what happened. So the Poisson distribution will tell us what is the chance or the probability of getting 0, 1, 2, 3, 4, any number of events when the average number per decade is 1.0. Of course, the event is a coast crossing of a very severe tropical cyclone. We're interested in knowing the chance or the probability of getting 4 crossings per decade, as happened in the 2010 to 2020 decade. That turns out to be 0.015, or 1 in 67. So if the climate is not changing with time, we call that stationary, we would expect that to happen once every 67 decades, or 670 years. So obviously a very rare event. Now you might say, well, what if the average turned out to be 1.5 instead of 1.0? Well, even in that case, we expect that to occur once every 21 decades, or 210 years. Still a very rare event. Well, now we'll look at some other trends. Previously, we looked at the number of severe and very severe tropical cyclones impacting the Queensland coast. Now let's look at all tropical cyclones, and not just those impacting the coast, but those that were in the ocean or the Coral Sea adjacent to the Queensland coast. So this bar chart here shows in blue the total number in the 5 decades from 69 to 2019. The blue shows the total number in the Coral Sea, and the red bars show those of them that actually made landfall. So these are all cyclones of all categories. So of course the numbers are quite a bit high here, but there does seem to be a bit of a decreasing trend actually in the total number of cyclones in the Coral Sea. Other people have observed this, but of course we're more interested in those severe and very severe cyclones. Now, staying with the cyclones in the Coral Sea, we'll narrow them down now to the severe cyclones, which on this graph were categorized as those with a central pressure at some time in their life less or equal than 950 hectopascals, which is approximately category 4 level for those same 5 decades. Now in this case there seems to be an increasing trend. The blue bar showing the total number of cyclones of that high strength in the Coral Sea. Of course, previously we talked about the landfalling ones being stronger, especially in the last decade. Now coming back to that footprint or contour plot of maximum gust when Cyclone Yasi impacted the Queensland coast back in 2011, it's quite clear that the contours, the wind speed on the contours reduces pretty dramatically once you get inland. So for example, if you're 50 kilometers inland as shown there, the maximum gust is down to 45 meters per second, which is actually less than half the wind pressure than would occur on the coast in that 10-kilometre strip. So this is a phenomenon that we've recently taken account of in the wind standard AS NZS 1170.2 by introducing a linear variation from the coast inland. Now the black solid line on this graph comes from data from the United States showing the reduction or the decay in wind speed as a function of distance from the coastline, or normal distance from the coastline. The black dash line is what we previously had in 1170.2 2011, where we had the step changes. So the first 50 kilometres there was no reduction. Then you had another step down for the next 50 kilometres. Whereas the data shows something different. It's continually decreasing. So you'll see the red line come up there, which is the new linear reduction that I just mentioned, which is in the 2021 edition of AS NZS 1170.2. Well, now we can draw some conclusions from all this information I've been talking about the last few slides. Based on the 50-year period from about 1970 to 2020, you recall that the value for 500-year average recurrence interval gust in 1170.2 of 66 meters per second corresponds to about 3.6 impacts of very severe tropical cyclones in a decade, whereas over the 50-year period it's been somewhere between 1 and 1.6. So this indicates that the standard is actually quite conservative based on the 50-year period. However, for the last 10 years, or the 10 years 2010 to 2020, that figure of 3.6 is about right. We had 4 impacts in that decade. So 3.6 is actually not too far off. So we shouldn't be complacent. If this is a trend going on here, then this might be a feature of decades into the future. In other words, the standard is not going to be that conservative. So there is this possible trend that the climate is changing due to global warming, and we are going to get stronger cyclones impacting that Queensland coastline. That's certainly consistent with the computer modelling of the effects of carbon dioxide increases on the climate. So what are we doing in the standard about that? We've introduced in the 2021 edition a climate change multiplier, MC, of 1.05 to account for future climate change. This is based on some of these numerical studies that I mentioned. But of course, this factor may be reviewed in the future. The other thing we've done with respect to cyclone impacts is to introduce this linear reduction in the regional wind speed with the distance from the coastline. All this is doing is reflecting the weakening of the cyclones. As soon as they cross the coast, they lose their source of energy, which comes from the ocean. Just finally, the last point there, this has been mentioned a few times, that maybe we shouldn't be looking at the gust wind speed at a point or at a building site, which is what I essentially have been talking about for the last this talk. Other people have suggested then if you've got a community, a town or a city on the coast, having a cyclone impact there affects the whole community. So it's more than just one point or one building site we're interested in, which is how we design structures. Well, this is certainly a legitimate issue, but it's not really an issue for 1170.2. It may in the future be addressed in the National Construction Code, where they may mandate that if your building is part of a larger group, a city or a town, then you need to design for a wind speed with a higher recurrence interval. So that's the end of the talk. I should mention this talk is based on a paper that was published in the Australian Journal of Structural Engineering a couple of years ago. So feel free to go and read the paper and get the full details.